Hi everyone, let me know if you can hear me. Okay, so I think everything is good, right? So let's just start. Now, this is the second part where we will be talking about CRC and then we will be talking about the network layer mainly. Okay, so let's just get started. First, let me know that how you are liking the sessions. If you want anything to be improved in the session, or there is something that I need to accommodate, let me know, and then we will start. So, how you all of you are doing? Okay, Namda, hi, good evening. Cool. Should we start now? So, if everyone is here, then we can start, right? Let me just get started. So, we were talking about the Hamming distance. Now, let's just continue with the same idea, and then we will see that like how the other formulas in the Hamming distance have been derived. So, I think we were talking about Hamming distance. Yeah. So one thing is very clear to everyone that if you want to detect just t bits of error, right? So there were two things that we have just discussed. One is that in the Hamming distance. See, one thing I can say that if you are attending this session throughout the day, which means we might wind up, at 11 p.m. So it might take some time, but if you are attending the sessions throughout the day, then definitely you will never feel difficulty in computer networks. That is what I can definitely say. Okay, you will be improving many of your concepts. There will be many concepts that you will be improving. Okay, so Lalit, hi, good evening. Hi, Pratik, good evening. So, okay, there is one user that is Uncle ALC. Is it hard for the average student to get 1000 rank? No, like, but if you just ask me, is it hard in just 5 days? Then obviously in the 5 days it is not possible. But yeah, like for an if you have put consistent efforts, maybe 3 to 4 months, then yes, 1000 get you can definitely get. Okay, thank you. So for the Hamming distance, we were talking about. Suppose that you want to detect t bits of error. Let me just write it here. Suppose if you want to, first thing is that detect t bits of error, then the minimum Hamming distance, okay, this is t. The minimum Hamming distance that you need is basically t plus 1. If you want to correct, okay, if you want to correct, let's suppose t bits of error, then the minimum Hamming distance that you will be having is basically 2t plus 1, right? I hope these two formulas are clear to everyone. Like how we are driving is not much important, but you also know that how we have derived these two formulas. Now let's just see that how to even construct the Hamming codes, right? How to construct Hamming codes. Now, most of you might be already knowing, so that's why I will just quickly tell you that how to construct the Hamming codes. Mainly, I am more interested in one formula, that the derivation of one formula, which is basically 2 power m is greater than equal to m plus r plus 1, or 2 power r is greater than equal to m plus r plus 1, something like this, right? So I'm more interested in that formula, that how, like why this formula makes sense. Basically, this formula makes sense. And what is this formula? So basically we will talk about this, that why this formula is making sense. Now let me move further. So this is the one question which is a very easy question. You can definitely answer this question. What they are saying, consider a code with only 4 valid code words. So these 4 valid code words are given. They have also given that code has the distance of 5. I mean, minimum Hamming distance between any two code words is just 5. You can also verify it. And even if they do not give you this, then also it should be clear from the code words that is given to us, right? These are the 10 bits. If you just check, the Hamming distance between these two is 5. Hamming distance between this and this is also 5, but the Hamming distance between these two is 10 basically, right? The Hamming distance is 10, but anyway the minimum Hamming distance is 5. If the code word arrive is this, then the original code word must be, yeah, that's a nice question. So let's just see that they are saying that these are the only possible code words. So the possible code words are this, right? Now let's just do this question. So these are the valid code words, right? Okay, can anyone tell me what is the answer here? And then we will see that why that answer is basically making any sense. So these are the valid code words, right? Okay. So these are the valid code words. Now someone is saying that you have just got this code word. You have just got this code word, which is obviously invalid code word. This is one invalid code word. Now what they're asking is very interesting. They're asking that like what is the corresponding, they are asking that what is the corresponding uh, yeah, what, this is the invalid code word. Now they're asking what is the corresponding valid code word. So the original code word. So basically they are saying this is the invalid code word and these are the valid code word. This invalid code word must have been from which valid code word? That is what they're asking. Can anyone tell me what is the answer? Yeah. Hello Vijay. Hi Dhruva. So just let me know what is the answer here. See what is happening here. These are the valid code words. Now you see the minimum Hamming distance is 5, which means you can detect I mean 4 bits of error, and you can if the correction is if you talk about the correction, you can correct up to 2 bits of error. So up to 2 bits of error you can correct, right? Because 2t plus 1 is 5, and which means t is basically 2. It means you can correct up to 2 bits of error, because minimum Hamming distance d minimum is given to you, which is 5, right? Now if you are having 2 bits like if you are basically having 2 bits manipulating two bits manipulation from this, then you can definitely correct it. So but if you check it, then it is a 3 bit away. So definitely this is not the valid code word, right? I mean, they are saying that if has been arrived, then what is the valid code word? See, the question is not very well framed, to be very honest. Like what they should have told is basically they should have mentioned is the code distance is 5. That is okay. I mean, that is still now, that is what the programmer has. I mean, this is how the programmer has designed their code, right? Now they should have mentioned that the channel has this is a noisy channel. They should have mentioned that this is a noisy channel. That is okay, but they should have mentioned the channel cannot produce the error more than 2 bits. That should be given to us. Okay, one line that should be given to us is that channel cannot produce errors more than 2 bits. Suppose it is given to us for now. Now, if channel cannot produce more than 2 bits, then obviously this is not the answer. Is this the answer? Then definitely this could be the answer, because this 1 1 is getting changed to 0 0. Is this the answer? No, this is the huge Hamming distance. This is also huge Hamming distance. So that's why this is the correct answer, right? Okay. So you can actually correct up to 2 bits of error, and you will say that this is the correct answer. So I think A is the answer, right? Yes. Yes, Narmada. So that is correct. So A is the correct answer, but they should have actually mentioned this a little more carefully in the question. But anyway, that is fine. This was a UGC net question, so maybe they have missed it, but that is fine. In GATE, most probably they will not do these kind of things. I mean, generally this should be a well-framed question, but anyway. Now let's see this question. What they are saying: to guarantee a correction up to 5 errors in all the cases, the minimum Hamming distance must be. If you want to correct up to 5 bits error, then what should be the minimum Hamming distance? Should it be 5 into 2 plus 1? Is it 11? See, don't do this mistake that that's not 11. You want to basically correct up to 5 bits of error. So basically D minimum you want to find out. Okay, sorry. Yeah, that is the answer. Correct up to 5 bits of error. Like if you want to correct up to 5 bits of error, then basically D minimum you want to find out. And to correct T bits of error, 2T plus 1, which is 11 is the answer. Yeah. So 11 is the correct answer. Yes, that is right. Let me know if you have understood this. Okay, cool. So yeah, A is the correct answer. Let's just move further. Now, that was a G question. Now let's just do quickly this question. This is an MSQ question. Let me know what is the correct answer. This might be a bit tricky, but anyway, let me know what is the answer. This is an MSQ question. Okay. So what they are saying, an error control code with the minimum Hamming distance of 11 is capable of detecting 11 bits. If you have minimum Hamming distance 11, then what you can do, D minimum is given to you, which is 11. Then if you want to correct, then you can correct up to T bits of error, which means you can correct up to 5 bits of error. If you want to correct, if you want to detect, then you can detect up to 10 bits of error. right? So you can detect up to 10 words of error, detect 11 is wrong, detect 5 is correct. Actually you can detect up to 10 words of error. Now 5 words of error can you detect? Yes, you can definitely detect. Yeah, right? I mean, you can detect up to 10 words, but you don't want to detect up to 10 words, you just want to detect up to 5 words. That's also fine. Correcting 5 words of error is also good. Correcting 11 words of error is wrong. So that's why B and C is the correct answer. Yes, that is correct. Nice. Let's just move further. So B, C is the correct answer. Now let's just move to the construction of Hamming code. So please let me know, please just let me know quickly in the comment box that how many of you does not know that how to construct a Hamming code. If you know this, then we can save just 10 minutes. Otherwise I can tell you. Okay. I mean, that's not a big deal. I can also tell you, but if you know this, then let me know. So suppose that I want to, I have some code word. Let's take one example. Okay. So suppose I have one data word and I want to construct the Hamming code. Okay. Suppose this is the data that I have, which is this one, and I want to construct the Hamming code. Then what is the idea to construct the Hamming code? What we will be doing to construct the Hamming code? We will be just saying that okay, if you want to construct the Hamming code, then you can use the parity bits, and where to put the parity bits, that is important. This is basically you can put the parity bit at the first place, which means you can put the parity bit here. You can put the parity bit here. I mean, see, let me just number them as 1, 2, 3, 4. Okay, this is the see this is the position number 1. This position number 2. Let's suppose. Okay, and this is position number 3. This is position number 4, 5, 6, 7, 8. Right. So let's suppose these are the position numbers. So we will be putting parity bits. Put parity bits in the position of 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, like that. So 2 power 0 means in the first position put the parity bit, in the second position put the parity bit, in the fourth position put the parity bit, in the eighth position put the parity bit. Now, someone asks you that why you are doing so. I mean, why you want to just put the parity bits on these selected locations. Okay, so why you want to put the parity bits on the selected locations? The answer is that, like, I mean, let's just do one thing. Let's just hold for 5 minutes, and then I will ask you the answer again. Okay, so there is a method that we are going to follow, and actually there's a like lot of mathematics behind it, but we will just get an intuition that why this kind of placement makes sense. Okay, so let me just put this in the hold, that why placing parity bits in position of 2. So we will answer this after 5 minutes. Okay, for now let's not worry about it. Now suppose that we want to put the parity bit, and these are the locations where we will be putting. So let's just call this as parity bit 1. Okay, this is, let's just call it parity bit 1. Let's just call it parity bit 2. Let's just call it parity bit 3, or maybe some people call it, see, this is the position 4. So what people do, people call it maybe they see, if this is 4, people call it 4. If this is 8, people call it 8. It is up to you how you are maintaining your notations. You can call it P1, P2, P3, P4, does not matter. You can call it based on this. If this is 4, you call it P4, like that, right? I mean, and anything you can do. Like, I don't know what to do currently, so I'm just doing P1, P2, P4, P8, but you can do anything. Now this will be a parity that will be based on, if it is 1, then it will be based on 1, and then skip 1. Skip 1 means skip 2, and skip 1 position, which is 2, and then 3, then skip 4, then 5, then skip 6, then 7, 9, 11, 13, like that, right? This is 8, 9, 10, 11, 12. This last position is 12. So I have till this point. Now this is basically saying that take 2, start from 2, 2, 3, skip 2. Skip 2 means skip 4, 5, then take 6, 7, then skip 8, 9, take 10, 11, right? And then skip 12, and then so on, right? This is saying take 4, start from 4, 5, 6, 7, skip 4, 8, 9, 10, 11, skip, and then take 12. This is saying that that take 8, start from 8, 8, 9, 10, 11, and okay, till 11 only we have. So basically it will be based on these bits, it will be based on these bits, it will be based on these bits, it will be based on these bits. But again, if someone asks you that, again the second question, okay, this is the first question that we have. If someone asks you that why P1 depends on 1 3 5 7 like that, right? Similarly, why P2 depends on this, then again we will answer after 5 minutes. So all of these that is coming to your mind, we will just answer after 5 minutes. Just hold on. Okay, so Narmada is asking, is parity bits always placed at the two place? Then answer is, it is your design choice. How you are designing, that's only that matter. Okay, the way we are going to construct the Hamming code is basically we are going to put at these locations. Now it is not necessary, but if you do it, then the things become very convenient. Okay, and what is that convenience it is bringing, I will just answer after 5 minutes. So why we are putting at these locations, and like I mean why we are placing parity bits at these locations, why P1 is dependent on this all is very much combinedly too much of related things, and this involves some of the mathematics. So I will answer I will answer few minutes later. Okay, now if you want to calculate P1, you can just say that okay, this you can just take this 3 and then 5 and then 7 and then 9, and then you can calculate this P1. I hope you know this, that how to calculate this P1 P2, right? So if you want to calculate the P1, like if you want to calculate this, it is dependent on this. So that's why that this will be 0. I'm using the even parity bits. Okay, and then this, if you want to position 2 check bits, position 2 will depend on 2 3, and then you skip 4 5 then 6 7 like that, right? Okay, so it will be dependent on this. Then you can calculate it, and then answer will be this one. And then similarly you can calculate this one, and answer is this. You can calculate this position, answer is this. So I do not need to calculate, you can easily do it, right? Now let's just see some analysis on this. Okay, so let's just see some analysis. Now this is a homework question. I mean you can easily do it. They are asking you to code it, so you can find the parity bits and you can place in the corresponding position. Now suppose if I say okay, they are calling it P1 P2 P3 P4, but let me just call it P1 P2 P4 and P8. I mean it is up to you how you are basically maintaining, but I hope that's fine. Suppose they say that if P1 and P2 fail, which means at the receiver end, if you check at the receiver end, then at the receiver end you found out that that P1 and P2 fail, which means P1 is saying that there is some error, P2 is also saying there is some error. Then what will be the answer? Which means like which bit has actually some error. Suppose that you say that P1 is having error. P1 is basically dependent on 1 3 5 7 9 11. P2 is basically dependent on okay. So P2 is dependent on 2 3, you skip 4 5 and then 6 7, and then you skip you skip 8 9 and then 10 11, right? They are saying that these two fail, which means they both are indicating error. Fail means they both are indicating error. What do I mean by that? That at the receiver end, whatever you are getting received, okay, see, you will send something, right? You will send your code word, which is, let's suppose this is one code word that you have. Okay, this is the final code word that you got. You send this code word, right? And when you send this code word, then P1 and P2 are indicating some error. Let's suppose this is the thing, this is at the center side, but you receive something else, and then they're saying P1 and P1 is this one, P2 is this one. They're indicating error means that they are not matching. I mean if you check all of these bits, then they are not having an even parity. If P1 is indicating error, that it means what? There must be error either at 1 or at 3 or at 5 or at 7 or at 9 or at 11. Okay, so let me take one smaller example. Probably let's suppose that there are only 3 parity bits, P1 P2 and P4. Only 3 parity bits. I mean, this will be a little smaller example, so you will get to understand more. Only 3 parity bits you have, which means whatever data that you have placed P1, you have placed P2, then some data bits, then this is the position 3, then 4, and then 5, 6, and 7, right? So suppose that you have some data which is something like this, right? I mean, the data is basically 4 bits, data is 4 bits, and the parity bits are needed is 3. Parity is 3 bits. Now, if I say, let's suppose here in this case, if I say P1 and P2 fail and P4 pass, so P1 fail means P1 is dependent on what? See, P1 is dependent on, if there are till 7 only, it is dependent on 1, 3, 5, 7. P2 is dependent on what? P2 is dependent on 2, 3, and 4, 5 you will skip, then 6, 7. They are saying that P1, P2 indicate error, and P4 does not indicate error. Okay, does not indicate error. Indicate error, which means what? You need to understand this very carefully, then you will get to understand everything behind this Hamming code. Okay, so let's just put a little focus here and let's just understand this very carefully. Suppose P4 does not indicate error and P1, P2 indicate error. So P4 is basically 4, 5, 6, 7, and then you will skip 8, 9, but till 7 only you have. Now P1 is indicating error means what? There is an error either at 1 or 3 or 5 or 7. There is an error either at 2, 3, 6 or 7. So what is common in both? Common is 3 and common is 7, right? So both of them combinedly will say there is an error. There is an error at 3 or at 7, right? Now they combinedly are saying both there is an error at 3 or 7, and this is saying that this is not indicating error. It means there is not any error. Okay, there is not any error at 4, 5, 6, 7, which means 7 does not have any error. Combinedly you will say, since 7 does not have any error, so 3 will have error, right? So basically what I'm saying, that if they tell you that okay, these things are having error, these things are not having error. Okay, thank you. Twinkle is saying that hello sir, I just completed watching the previous session of network marathon. The way you explain is so good. I don't feel like using the formulas and understanding the concepts. Thank you so much, Twinkle. And if you really feel that the sessions are good, then just please hit the like button so that we get more recognition. And also put a comment after the video, after the session is end, so that like others also get to know that what is the state of this session. Okay. So if you check this P1, P2, then they are saying that that there is an error at 3 and 7, 3 or at 7. But if you check this P4, this is saying that okay, 4, 5, 6, 7 does not have any error. It means 3 will have an error, one error. So basically, now just understand very important thing. P1, P2 fail. It is telling you that position 3 is having an error, right? Position 3 is having an error, right? Position 3 is having an error. Now let's take another example. Suppose P1 and P1 and P4 fail. Okay, let's suppose these two fail. Then in which bit I have the error? I'm assuming that I just have one bit of error. So the way we are constructing the Hamming code is basically like you can construct for the higher bit of the error, but the way we have in our syllabus is basically just for the one bit of one bit of correction. Okay, because the way we construct is basically d minimum that we have is actually 3. Okay, I mean minimum Hamming distance is 3. See, the parity bits, the way we are putting the parity bits at different locations, or whatever way we are doing, actually make sure that d minimum is 3. Okay, we have actually done it in our course, but today we do not need to feel like proving it. But yeah, you can also prove that d minimum is 3 in our Hamming code, the way we are constructing the Hamming codes. Okay, cool. So P1 fail, it means 1, 3, 5, 7 error. One bit of error is either in 1, 3, 5, 7. P4 fail means 4, 5, 6, 7. Now both of them combinedly agree that either 5 is having error or 7 is having error. Now if these two fails and like other one is obviously passing, I'm not writing it, but it gets passed. Let's suppose 2, 4, then 5, 6 have error. Sorry, 5, 6 skip, then 6, 7. So it is saying 5 or 7 have error, but it is saying that 7 does not have any error. So combinedly you will say, combinedly what you are going to say, you are going to say that 5 is having error, position 5 is having error, right? So basically, if P1, P2 fail, then you will say that okay, position 3 is having error. If P1, P4 fail, then you are going to say like position 5 is going to have error. Actually, you can just add this two, and then you will be getting the answer. 5 is having error. Add these two, 1 and 2, 3 is having error, right? So you can just add them. So in short, you can also put something like this: P1, P2, P3 or P4, whatever you want. Now, if it is indicating, let's suppose it is indicating error, it is not indicating error, it is indicating error, then the position 5 has error. Position, okay. So if you convert this binary to decimal, then you will be getting that 5 is an error. Suppose that this is indicating error, this is indicating error, but this is not indicating error. It means position 3 has error. Okay. Suppose that this is indicating error, this is indicating error, this is indicating error. It means that position 7 has error. Okay. Is this fine to everyone? Now from here you will get to know many things. Okay. Just from here you will get to know many things. Let me know if that is fine to everyone. Yeah. So thank you Narmada for commenting, and thank you Twinkle. So like in the earlier session, some of the people has commented. So I really want to thank them because it really means for us, because we are just starting. And then if you, I mean, we have just started teaching like online, and if you just put a either a thumbs up or you just comment it out, then other people also get to know. So that's how like people get to know about us. So that's why I really want to thank everyone who has actually commented out. Yeah, thank you Pratik, thank you so much. So Pratik also done some comment. Now, basically, you need to understand that every position, every combination is telling you the exact position, that which position has error, right? Every combination. If P4 indicate error, P2 does not indicate error, P1 indicate error. See, P1 1 here, if I'm writing 1, does not mean that P1 is 1. It means that P1 is indicating error. Okay. P1 1 does not, it is actually not P1. I mean, like, how should I write it? It is not P1 first of all. P1, if I'm writing 1 here in the below this in the column of P1, it means that P1 is indicating error. Okay, this one means this one means that P4 is indicated. P4 could be 0. In reality, P4 could be 0. Okay. Now every combination is telling me the exact position where is the error, right? Or in the shortcut, what you can do, whatever is indicating error, you can write it in binary and then decimal, or maybe you can directly add this 4 plus 1, right? Like that, you will be getting 5 like that, right? Okay. Now there are a couple of questions that you might be having, that how this magic is happening. I mean, how I'm like, if P1 P4 is indicating error, then how I'm sure that that position 5 has an error, right? So how all of this is working so nicely, which means that how I am able to say that if P1 and P4 indicate error fails, basically, then error is in position 5. How? Why this kind of thing is making sense? Why this makes sense? This is my question. Let's just answer this question. Do you remember that P1 is dependent on what? It is dependent on, let me just go to the next page. P1 is dependent on, let me do one thing. Let me write here 1357, right? It is dependent on 1357. Can you quickly represent this 1 in 2 power? This is 2 power 0. This 2 is basically 2 power 1. 3 is 2 power 1 plus 2 power 0. And then 4 is 2 power 2. 5 is 2 power 2 plus 2 power 1. Sorry, 2 power 0. 6 is 2 power, this is 4 plus 2. 2 power 2 plus 2 power 1. And then finally 7 is 2 power 2 plus 2 power 1 plus 2 power 0, right? This is 7. Now see that P1 is dependent on this. P2 is dependent on what? It is dependent on 2, 3 and then 4, 5 you skip, then 6, 7. Then P3 or P4, whatever you want to call. Okay, this is dependent on 4, 5, 6, 7. Right? Now you notice one thing is that P1 is dependent on something which is actually 1, 3, 5, 7, which must be having 2 power 0 as a factor, right? 2 power 0, 2, see, this is the dependent on 1, 3, 5 and 7, right? P1 is dependent 1, 3, 5, 7. In everywhere, I have 2 power 0, 2 power 0, 2 power 0, right? So P1 is dependent on all of this, which is having 2 power 0. So P1 is dependent on all positions that has 2 power 0. Is this clear to everyone? Let me know. Right? Let me know if this concept is clear to everyone or there is any confusion. If this is clear, then we can move further. So P1 is dependent on everything which is having 2 power 0 in it. Similarly, P2 is dependent on something which is having 2 power 1. See, this is 2 power 1, right? See, it is dependent on 2. 2 is having 2 power 1. 3 is having 2 power 1. 6, 7. 6 is having 2 power 1. 7 is having 2 power 1. Right? So P2 is dependent on all which is having 2 power 1. Depends on all which is having 2 power 1. Now, P4 is depending on all which is having 2 power 2, right? Depends on all which has 2 power 2 in it, isn't it? Let me know if that is clear to everyone. Now, if that is clear, then we can see that what to do. See, now it is depending on like P1, P2, P3, and these are depending on this. Now, suppose I say that P1 and P2 fail. It means that whatever got failed, right? So whatever got failed, that position must be having. See, P1 is dependent on everything which is having 2 power 0, right? That must be having 2 power 0 as a factor. That must be having 2 power 1 as a factor, because it is there in the 2 power this P2 and it is there in the P1. It is not in the P4, right? Not in the P4. It means it must not be having 2 power 2 as a factor. 2 power 2 must not be there, which means the only term which satisfy all of this is basically just 3, right? That has this 2 and does not have this one, so that is 3. So that's how it is working actually. Now, if I say that suppose anything, okay, suppose P1, P4 fail and P2 pass, then it must be having 2 power 0 as a factor, must be having 2 power 2 as a factor, must not be having 2 power 1. It means it must be 5. So position 5, right? So that is how it is working, which is very nice. Which is very nice mathematics finally. Okay. So is this clear to everyone? So that's how it works. Now you may ask me that this question, let me go to this question that which I said like we will answer 5 minutes later. That why we are placing in power of 2. So basically, or why P1 depends on 1357. Actually, all of this, whatever we are doing, all of this is to make sure that our life get easier, which means that if I do all of this, which means if I place at those particular locations only, if P1 is dependent on only 1357, right? And then these are placed at those position, and P1 is dependent on 1357, P2 is dependent on like that 2 3 5 6 like that, right? Then I can say that this mathematics works. So if I do all of this, then if P1, if I write P1, P2, P4 or P3, then let's suppose this indicate error, this does not indicate error, this indicate error, then this mathematics works. That then I can directly say it is 5. If I do this, see, if I do all of this where P1 is dependent on this only, P2 is dependent on this only, right? And that is how I combine all of this mathematics, all of the intuition, then finally this kind of mathematics works. So this is working just because P1 is dependent on 1357, just because P2 is dependent on 2, 3, you skip 4, 5 and then 6, 7, right? And P4 is dependent on 4, 5, 6, 7. Just because of this kind of arrangement, this kind of placement, this kind of mathematics is working actually. I just told you the intuition why that is the case. Where is the intuition? This is the intuition, right? This is the intuition. So this is the intuition that P1 is dependent on the position that is having 2 power 0, P2 is dependent on the position that is having 2 power 1, right? Let me know if you have understood this. So just to make this kind of mathematics easier, it might seem that okay, it is not a big deal, but actually it is a big deal, right? I mean, your life got very easy. You just need to know, okay, P1, P4, then 1 plus 4 is 5, right? Cool. I hope you understood. Now, let's take one takeaway from this and then we will move further. Then I will drive you one formula, which is this. Now, let's take this as a takeaway, which is that every combination of P1, P2, P4, okay, it is 110, 101, 001 or 011, 111, whatever, right? Every combination of this tells me exact position where is the error. Suppose that I have 000, which means no one is indicating error. Then where is the error? Which position is having error? Can anyone tell me? If no one is indicating error, then there is no error actually, right? So there is one very good takeaway that we want to take, and that will actually be with us to understand the Hamming code more clearly. Now, let me ask you one last question. Suppose it is 010 or maybe 0 or maybe 1100. Suppose if this is having error, it means only position 2 has error. Position 2 means P2. Position 2 is actually the P2 position, but anyway, position 2 has error. It means position 4 has error, right? Position 4 has error. So basically, if I just say that if I just say that where you want to, I mean, if I just say that that these are the positions which are indicating error, these are the positions which are not indicating error, these are the parameters which are indicating error, these are the parameters which are not indicating error, then you can tell me the exact position where is the error, right? So basically, every combination, the takeaway that I want to take from this particular slide is this one. Every combination of P1, P2, P4 tells us exact bit where the error occurs. This is very important takeaway concept. Why it is important, I will tell you. Actually, just using this concept, we will drive you one formula, which is 2 power r is greater than equal to m plus r plus 1. I will drive one formula just using this takeaway. Okay, cool. Now let's just move further. Is this takeaway clear to everyone? Okay. Now let's just do this question and then we will write the formula. Can you tell me what is the answer here? Okay, let's just see what is the answer. What they're saying is that how many check bits, check means parity bits, okay, check or parity are same. How many check bits or parity bits are required for 16-bit data word to detect 2 bits of error and single bit error correction? See, one thing I want to make clear is that whatever we just did, okay, whatever we just did to construct Hamming code which means, I mean, this kind of construction, just yeah, this kind of construction, that it depends on this or whatever, right? So whatever method we just used to construct the Hamming code, which is this one, which is actually, let me write it here, which is this one, this method, whatever we just use, that okay, this position, I hope that is visible. Okay, so whatever method we just use, that position 1 depends on this and this, whatever, right? Whatever method we just use to construct the Hamming code, basically has d minimum having distance to be 3. Now we are not going to prove it. We did it in our course, in our full length course, but today it is not required. So that's why I'm skipping something, okay? Because it is absolutely not required. So basically it has the minimum distance of 3, which means the way we have constructed the Hamming code, okay? Which means the way we have constructed the Hamming code, the Hamming code has d minimum is equal to 3. It means that it can detect up to 2 bits of error or correct 1 bit of error. Now if someone asks you, can you have a Hamming code that can do even better things, that can be more powerful than this Hamming code, then answer is yes, we can definitely do it, right? Okay, so if someone asks you that that can you do it, I'm audible, right? Let me know if I'm audible. So if someone asks you that can you do something which is basically which is driving you the Hamming code such that your d minimum is 5 or maybe 7 or maybe 10 or 11 or something, then we can definitely do it. But for our GATE syllabus, this is the only way we know. Okay, so let's now do the questions. See, in this question, in this question so in this question they are saying that you want to detect, you want to make the Hamming code that is detecting 2 bits of error and correcting single bit of error. Now aren't they hinting you that you use the same thing that you have just used, right, using the Hamming code? So basically they are saying detect 2 bit of error and correct and single bit of error correction. It means you just use the same thing that you just you use the same thing that you just did. So basically they are just saying that you can do the same thing which you just did. That's the only thing they are saying, which means you can construct your Hamming code in the same way that you just did. Now they are saying how many check bits are required for 16-bit data word. Okay, so what do it mean? What does this mean? So they are saying how many check bits are required for 16-bit. How many check bits are required for 16-bit data? This is what they are asking, right? Okay. Now let me tell you. Suppose they ask you that number of parity bits. Okay. How many parity bits are required if the data bits is, let's suppose, just 4? Then what you will say? You will say, okay, these are the 4 data bits. You definitely need P1, P2 here, and then you will be putting one data bit here, right? And then you will be having P4. Then you can put 5, 6, 7, and then there will be P8, right? So you can put 3 here, 1 here. So basically, yeah, you can put 4 here, and obviously at the end you do not need parity bit because it depends on 8 and the right numbers, right? It will depend on 8 and 9, 10. So it like there is no point in having P8. So basically, like just to have three data bits, you must be having 3 parity bits. Sorry, just to have 4 data bits, you must be having 3 parity bits. So here the parity bits required is 3. Let me know if you have understood this. Okay. So learn with me is saying that hi, I'm late to join. So see, if you're late to join, then maybe you can just skip 5 or 10 minutes. We are moving to the next topic, okay, after 10 minutes. So let me just continue here. Now, what we are saying, that if the number of parity bits, if the number of data bits has 4, then you need 3 parity bits, because then only you can put your four data bits here. One is here, another one is here, another one is here, another one is here, right? Okay. Now suppose that number of parity bits they are asking, parity bits, and then they are saying that data bits are actually, let's suppose something 10. It means P1, P2 you can put here, you must be putting here just for one data, and then P4, then 5, 6, 7, then P8, right? And then 9, 10, 11, 12, 13, 14, 15, and then P16. So basically, just check here, are 10 done or 10 is not done? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10 is done till this point, so you don't even need P16, right? So you will say that your answer is, if 10 is done till this point, your answer is 4, right? Is this fine to everyone? Now, let's just answer the same question where they are saying how many parity bits are required if your data bits are 16. Okay, you want to put 16 data bits. So how many parity bits are required? That's what the question is. So let's just solve this question. See, if you want to put 16, then till 1, 2, 3, 4 you have put here, 5, 6, 7, 8, 9, 10. Okay, 8, 9, 10, 11, 12, 13, 14, 15, and then 16, P16 will be here. And then 17, 18, 19, 10, I think there, and after many long it will be P32, but that's okay. So 1, 2, 3, 4, 5, 6, I mean definitely there will be 16. There will be 16 data bits you can definitely accommodate, right? 16 data bits. So how much you need? 1, 2, 3, 4, 5. 5 you need, right? So what is the answer? 5. A is the answer, isn't it? Let me know if you have understood this method. See, we can solve this question using many methods. I think using 3 to 4 methods we can solve, but this is the most intuitive way that came to my mind and I just told it. But suppose they ask you, suppose they ask you that, okay, what is the answer if the number of data bits are maybe 500? Okay, I mean if they say what is the answer if the number of data bits, let's suppose, is 500, then will you be doing the same method? Will you be checking that, okay, what to do, what not to do? I mean, like that, I mean, how many are there, how many are not there, or there could be some formula directly? There could be some formula, right? So suppose they say the data bits are 500, then how many parity bits you require? So let's just see one formula which is basically like this. So now the question is that number of parity bits we need, number of parity bits we need. Here it is given number of parity bits we need. Here it is given. Let's suppose that number of parity bits is R, and we want to calculate this R. Okay, R. What is this R? And the number of data bits is given to be let's suppose M. Number of so total bits equal to M plus R. Total is M plus R, not plus 1. Sorry about it. M plus R. Let me just call this total bits as N. Okay, so N is M plus R. Now they are asking about the R. What is this R? They are asking R for this M. Okay, for R for M. Is this question clear? So there is one formula which is basically this: 2 power R is greater than or equal to M plus R plus 1. It should be greater than or equal to M plus R. Now let's just see that why this formula is making some sense. Okay, so let's just see this why this formula is making some sense. Now, do you remember one takeaway? Do you remember there was one very important takeaway that I told you to remember, which was this one? Sorry, not this one. Yeah, this one. And I told you that we will be actually coming up with the formula using this takeaway. Now this is the takeaway which is saying that you will be having, like, for every combination of P1, P2, P4, or for every combination of the parity bits, it will tell you the exact position that where is the error, right? So this was the takeaway. Now we have R parity bits, which means that let's suppose these are the R parity bits. I mean, this will be actually not at the prefix. I mean, this will be in the mix of the data, but just for the sake of example, I'm saying this is parity, this is data. Okay, these are the R parity bits, and let's suppose this is M. Obviously, these are the intermixed, right? That's what you know how to place. So Sumant is asking that how to know data bits equal to 16 means include parity bits or without including. No, it will be given. Okay, it will be given. So data means only the data. Okay, data means only the data. And they will say code word bits. Code word means that it is including the parity bits. Okay. So now, if parity bits are R and data bits are M, then what does this mean? That there are 2 power R combinations that I have for the parity bits, right? 2 power R combinations for these parity bits. Each combination will tell me that, okay, whether there is an error here, there is error here, there is error here, there is error here, there is error here, error here, error here, here. I mean, error is at which position? So if there are 2 power R 2 power R combinations, which means let's suppose the R is let's suppose 4 or something, which means if there are 4 parity bits, then there are 16 combinations, right? There are 16 combinations. Each will tell me that where is the error. Okay, so basically, if this is 0 0 0 0 0 0 0 1, like that, if you are having 1 1 1 1, then this combination will say there is no error. This combination will say error is at first position. This combination will say that error is at which position? This is 2 power 4 minus 1, which means error is at 15th position. So basically, every combination will tell you something, isn't it? Now, how many combinations you have? 2 power R combinations you have. So basically, these are the 2 power R combinations. Every combination will say that error is at which position. Okay, error is at first position, error it is at second position. So every combination will tell me error is where. Now, how many positions do I have? How many? If this is M plus R is the total length, then how many positions I have? M plus R positions I have, and one combination will be no error. If there is no error, so basically I have total M plus R plus 1 combinations where I want to check that, I mean, I want to have these many combinations basically, right? So see, whatever number of combinations that I have, I want to have at least M plus R plus 1 combinations. If there are more combinations, I do not care. I do not have any problem. But I see, given any code word which is having length M plus R, okay, which is having length which is M plus R. Now it can be converted to no error. It can be as it is. Okay, it can be having, okay, there is only one bit of error, only one bit of error. Right? It can be, you can say there is no error. It can be error at first position. It can be error at second position. So there are total M plus R plus 1 combinations. Among them, I want to basically differ that which position is currently I have just received. Which means that if I am sending some data word, which is some code word which is having M plus R length to the receiver, let's suppose this is the receiver, then receiver can detect it as it is, which means no error. or receiver can detect with 1 bit of error, right? Because that's what I'm assuming, that my channel can produce at most 1 bit of error, right? So receiver can detect it maybe at most 1 bit of error, which means error at first position, error at second position, like that, right? So receiver can detect total how many combinations? M plus R plus 1 combinations. Now using the parity bit, I should be telling to the receiver, okay, or the receiver should be able to identify using the parity bit only that which combination it has received. That either there is no error or error at the first position or error at the second position, like that, right? So receiver should be able to identify that what it has just received, because receiver doesn't know that what it has received. It can receive out of M plus R 1 possibilities, M plus R plus 1 possibilities, it can receive any of the possibility, right? Because I'm assuming my error could be at most 1 bit. So that's why out of M plus R plus 1 possibilities, it can receive any of the possibility. So since it can receive any of the possibility, that is why it should be able to identify that which possibility it has. So there are R parity bits that I have, which means 2 power R combinations that I have. So these combinations should be, each of these combinations should be telling me that, okay, like if it is 0 0 0, I mean one of the combination is 0 0 0, then no error, right? And one of the combination is 0 0 0 1, then error is at first position, like that. So basically this should be enough combinations that I should be having, and these are the positions that I mean these are the all choices where I want to make a distinguish that that which choice I have just received, and that distinguishing can be done by the parity bits only. So I have 2 power R combinations, right? So here using the parity bits, let's suppose R equal to 50, okay? Which means I have 2 power 50 combinations, okay? This combination will tell me this, if I just receive, let's suppose 0 0 0 0 0, this combination will tell me that see, there is no error, okay? This combination will tell me, let's suppose it is 0 0 0 0 0 0 1, let's suppose this combination is also telling me there is no error. That's fine. I mean, that's fine. If there are too many of combinations, multiple combinations are telling me same thing, that's fine. I mean, that's fine. I mean, let's suppose multiple combinations are saying no error. I'm good with that. I do not care. I mean, if multiple combinations are telling me, as long as every combination is covered, I mean, every possibility is covered, error is at first bit. Let's suppose multiple combination is saying error is at first bit. I'm fine with this, right? But everything should be covered. Error is at second bit, error is at last bit, everything should be covered. Suppose that no combination is telling me, no combination is detecting this error is at third bit. No combination is detecting error is at third bit, then this is of no use. So basically, whatever combinations that I have, which is 2 power R, that should be good enough to tell me which combination that I have, which is M plus R plus 1. So here, see, at the receiver end, I have M plus R plus 1 combinations that receiver can receive, M plus R plus 1 combinations, and these parity combinations are 2 plus, 2 power R. These are 2 power R. So basically, whatever combination I have 2 power R, each of this combination should be able to tell me that that which particular configuration that I have just received. Okay, that's how it works. Okay, so basically 2 power R should be greater than or equal to M plus R, right? Maybe let's just do one question, it will be more clear, but before that, let me tell you one more thing, some intuition. See, suppose that R is 3, okay, and M is 30, which means you have just 3 bits, okay, 3 parity bits, P1, P2, and then P4, but you have many data bits. See, using these 3 parity bits, you can just cover how many combinations? 8 combinations. 8 combinations means that one of the combination will be no error. Effectively, you can tell the errors in the 7 bits. You can tell error here 1, 2, 3, 4, 5, 6, 7. So basically, if error is till this point, then only you can tell. If error is in this bit, you will not be able to tell. If error is in this bit, you will not be able to tell, right? So if error is in other bits, you will not be able to tell. That's the problem with too much of large M. So if M is 7 only, then yeah, that's a perfect fit, right? That's a perfect fit. Why? Because if M is 7, then I can tell the error in this bit, this bit, in this bit. I can tell error in every bit. sorry, m is 4, m is 4 means data bits. That if data bits are 4, then I can tell error in every bit. But let's suppose if data bits are 5, then and parity bits are just 3. Okay, parity bits are just 3 and data bits are 5, which means that I can tell error in this first data bit, second, third, fourth, but I will not be able to tell error in this data bit because I will be adjusting my combinations. Okay, cool. Now let's just see some of the questions. Maybe you will be getting the crystal clear idea after the question. Okay, let's do this question. This question I have taken from MIT, and this is very nice question to make you understand everything that we have just studied. So this question is little advanced in the sense that you will be getting you at the first sight you will be thinking that it is tough, but actually it is good enough to clarify everything that we have just studied. Now they are saying let k be the minimum number of parity bits needed to correct all t bits of error. See here they are saying t bits of error. See, earlier we used to correct only one bit of error, right? Then there were m plus r plus 1 combinations at the receiver side. Now they want to correct up to t bits of error. Then which of the following conditions must satisfy? Okay. See, then at the receiver side, you might be having no error. You might be having 1 bit of error. Now in this case, you might be having 2 bits of error. Similarly, you might be having t bits of error at the receiver side. So there are many possibilities at the receiver side. How many? This is just one. This is 1 bit of error. Let's suppose the n is the total number. So nc1. Now the error could be at any bit. nc2 error could be at any 2 bits. Similarly, nct. Okay, error could be in any t bits. So basically, these many combinations that you have at the receiver side, which is basically combinations at the receiver side means that you might be receiving any of this combination, maybe no error, 2 bits of error, 3 bits of error, like that. So combinations at the receiver side is basically 1 plus nc1 plus nc2 plus nct, right? Now combinations that you have using the parity bits is 2 power r only, right? Or 2 power k, here the k is given. Now these combinations should be greater than or equal to whatever combinations you have at the receiver side, right? So now tell me what is the answer. Yes, Aditi, that is fine. D is the answer. So that is very nice question, and if you understand this clearly, if you have understood the method clearly, then you must have got it that D is the correct answer, right? Okay, great. Now let's just move further. Good. Now let's do this question. This question has been asked in GATE 1992. What they are saying is this one. Consider a 3-bit error detection and 1-bit error correction Hamming code for 4-bit data. So before that, let me take some doubt if you have any doubt. So Kanak is asking, how do we get to know if D minimum is equal to 3 in the previous question where it was not mentioned bits to detect and bits to correct? No, it was mentioned in that ISRO question you are talking about. I think it was mentioned that they want to detect 2 bits and correct 1 bit. Right? It was mentioned in that question. So they should mention it, otherwise you will not get to know, obviously. Okay. Let me know if you have understood this question. See, if you have understood this question, then you actually have understood the Hamming code, and now you can solve any of the Hamming code related question. This question is just telling you that you have actually understood everything. Right? Okay. Now let's solve this question. Consider a 3-bit detection and 1-bit correction. 3-bit detection and 1-bit correction, and then they are saying having code for 4-bit data. Now data is 4-bit and they want to detect 3 bits and correct 1 bit. If they want to detect 3 bits, then they must be having minimum having distance of 4. They want to correct 1 bit, then minimum having distance should be 3. So since they want to do both, then you should take the maximum. So answer should be 4, right? Then the extra parity bits they are asking first of all. So you can use this formula, 2 power r is greater than or equal to m plus r plus 1. So m here is 4. So 4 plus r plus 1, 2 power r is greater than or equal to. Obviously, r equal to 2 will not satisfy. R equal to 3 is satisfying, right? So here it will be 3. Extra minimum, the minimum extra parity bits basically. The minimum extra parity means the minimum extra parity bits. Because the more if I have, that will not harm me. So you can say the minimum extra parity bits. I mean, it should be the minimum only. Okay. Required would be 3 and 3-bit error detection is possible because the minimum having distance should be the 4. Then only you can have the 3-bit error detection. Right? So I hope you understood. That was easy question only. Again, this is easy one. You can do it. The minimum having distance is 2t plus 1. So you can correct up to t bits of error, right? Okay, these are the easy questions. You can do it probably. Yeah. Now let's just move to CRC, and then once we finish the CRC, then we can move to the network layer. Let me know if there is any doubt in the Hamming code. So we are running little late behind our schedule, which means I was thinking that we can cover this CRC by 6:40 or something. But yeah, we have just started the CRC, so maybe my estimation was not good. But anyway, let's just continue. Okay, so CRC is also a block code. Block code means, like, if you remember, there are data bits, there are parity bits. That is called block code. Parity bits you can append at the end or in the between. Okay. Now, how does the CRC work? Most of you might be knowing that we are having a divisor, and then what we do. So let's suppose that there is a divisor. Okay, there is a divisor. We also call it generator, which is 1011, and then there is what we call it. This is a polynomial, basically a data word. Okay, data, that is 1001. Let's suppose this is the case. Okay. Now divisor could be of any length and data could be of any length. It's not necessary that data should be of equal size of divisor or something like that, right? Now what you need to do, if you want to divide it, then first you need to actually append. If divisor is a 4 bits, then you need to append the 3 bits, and then you can divide it, right? And then you can have your answer, and then finally whatever is the remainder, you just replace it here, right? So let me know if that is fine to everyone. I mean, if you already know this, or should I tell you? I think this calculation is fine to everyone, right? If like, this is just a CRC calculation. So at the receiver side, what we do? At the receiver side, we divide by the same divisor. If there is some data word get corrupted, then it will say error. Otherwise, it will not say error. Okay. Now here in the CRC, adding and subtraction both are same, which means if you say 1 plus 1, then also it is 0, because you actually do the JOR operation here. Or you do 1 minus 1, it is also 0. Basically minus 1 is same as plus 1 in CRC. Now in terms of polynomial, if I just write x cube plus x square, this is one polynomial, and that, let's suppose I want to add it to maybe x cube plus x, then it will be 2x cube plus x square plus x. But here this is actually in the binary, it must be 1 followed by like 3 0 or something, right? And then this is 1 followed by 3 zeros. Basically here the 2 does not make any sense, so actually it is 0. Okay, it is just x square plus x. In terms of polynomial also, it is x square plus x. You can do the binary also, it is x square plus x. So basically here the plus and minus both are same. Okay, and if it is 2, then it is 0. Now let's come to the most interesting part, which is the CRC code analysis, right? So let's just do the analysis of the CRC code, which means, have you seen these kind of questions? Let me quickly go through that question. Have you seen these kind of questions that 1 plus x is a factor of that, and those analysis type of questions that will you be able to detect some error or not, or something like this, right? Let me know if you have seen those kind of questions. This one, and maybe there are others also, right? This one, yeah, this question is quite popular question, which means that here I mean a lot of the students are not able to understand this question. So we will be solving all of the analysis type of questions where you need to know that how does the CRC actually works. Okay, so we like there are two type of questions they can ask in CRC. One is that just a division. Okay, another is that they can ask you based on the analysis type of questions. Division, I will be just doing one or two questions maybe, but we will be mostly focusing on the analysis type of questions. Okay, let me know if that kind of thing is fine to everyone. So let's just continue and let's just see that how does the CRC work. Okay. So let's just say that whatever the data word I have, it is just dx. Whatever the code word that I'm going to send, it is cx. The generator is gx, generator or the divisor is same, and the error is ex. So what do I mean by that? Let's suppose you send something which is x cube plus x. Now you get error at the third position or maybe at the x square. So this is the cx that you send, and let's suppose you receive let me write in binary for now, because you will get to know that what I'm doing. So basically this is x power 0 is just 0, x power 1, x power 2, x power 3. This is in binary. Now let's suppose this bit get corrupted. You are sending 1010 and then finally you receive 111110. Okay, this bit get corrupted, let's suppose. Can you represent that in the polynomial again? So this is that what you are sending. This is the, let me just call it a sending code word. And this is receiving code word. At the receiver side, you are receiving, let's suppose, x cube plus x square plus x. Is this fine to everyone? If this bit get corrupted, then you will be receiving this, right? Now let's just see that what is the relation in the polynomials. See, if this bit get corrupted, which means x square bit get corrupted, x power 0, x power 1, x square. If x square is bit getting corrupted, then you are essentially adding the x square, right? So basically, there is always a relation that is something like this. Receiving code word is actually equal to sending code word plus error, ex. Let me just call it error. So for example, let's just take one more example. For example, let's just say that you're receiving, you're sending code word, could be, let's suppose something. Okay, maybe let me take something else. Your sending code word is maybe 10. Yeah, so your sending code word is 101. Okay, earlier it was 1010. So let me just call it 11010. Okay, whatever. And then you are this is the sending one. And let's suppose there is an error at this position. This one gets changed to 0. Okay, see, earlier I made this 0 to change to 1. Now I'm making some 1 to change to 0. So, or maybe let's just take multiple ones. Let's just take this and this. These three are error. So what you will be receiving is basically 0 1 1 0 1 0 0. This is what you will be receiving. This is receiving one. Just represent this in polynomial. This is x power 0, x power 1. This is x power 2, x power 3. This is x power 4, right? So it is x4 plus x cube plus x. And what you are receiving is basically this 0 1 x square x cube. You are receiving x cube plus x square, isn't it? Now the error must be x power 4, x power 2 and x power 1. See, x power 4 plus x square plus x power 1. If you add this x power 4 plus x square plus x power 1 in this receiving one or the sending one, does not matter. Actually minus plus here are the same. You send it here, does not matter. You add to the sending one, you add to the receiving one, does not matter actually. But yeah, if you add to the sending one, then aren't you receiving it? Which means x power 4 plus x power 4 will get cancelled out because plus minus here are same. 2x power 4 is just 0, and then x cube plus x square plus x will get cancelled out, and this is just 0, right? 2x is just 0. Let me know if you have understood this. So are you all convinced that receiving code word and the sending code word has this relation, which means receiving code word equal to sending code word plus ex? Is this fine? Okay, if that is fine, then let's just move to the next thing. So here I am saying that receiving code word and sending code word are actually related with some error. Basically, if this is the receiving code word and if this is the sending code word, then both are having this relation. Okay, you can have any receiving code word and whatever sender code word, you can definitely error the corresponding polynomial, that is the error polynomial, and then you can get the receiving or the sending code word. Vice versa is also true because minus and plus here are same. The sending code word is equal to the receiving code word plus the error, right? Okay. Now let's just see that how all of this mathematics work. See, receiving code word is basically okay. They are saying it instead of sx, they are saying it's c. Does not matter. So let's just call it c. They are saying the receiving code word is basically sending code word plus error. Now, as you know that we are going to divide the receiving code word with the gx, which is the generator, and this generator if you divide with the cx, then it will always be 0, right? It is always 0, and then it will get remain. The remainder will be this, right? Yeah. Alok is saying one of the previous year question asked and and you have commented on Geo. Yes, on my time in the GATEOverflow, like no one was there to explain all of these concepts, so I had to figure out by my own, and then I just put it on Geo so that other people can also understand. So Sahil is saying exactly. Yeah, Sahil might have also seen that in my comment or my answer. So there is one user learn with me. It is saying why we are cancelling out same x powers. I'm not getting. Please clear. Yeah, so basically in binary, we perform XOR. In CRC, this is the mathematics that works. So in CRC, we do mod to mathematics. That's how the CRC is designed. Now, if you take the same corresponding binary, if you are saying x cube plus x cube, I am saying it is 0. Why? Because if you take the corresponding binary, then it will be the corresponding binary, right? So this is basically 1 and 1. Take mod 2, it will be just 0. So the corresponding binary I want to perform in the polynomial form. That's all. Okay. Because in CRC we perform the mod to mathematics. Now let's just check if we can proceed from here. So basically whatever we are receiving is actually C plus E, and then we will be dividing by GX definitely. Then we will be checking whether the remainder is 0 or not. So this will be the 0 remainder. This will always be the 0 remainder. Now, if this is 0, then remainder is 0. If this is not 0, then remainder is not 0. So basically, I can say the receiving code word, if I divide by gx, then it is same as sending code word dividing by gx plus error dividing by gx, because that's how the receiving code word, sending code word and error are related. Now this is always 0. That's what I'm saying, which means that I'm getting this one. I'm getting this. Okay. Now, if this is 0, if this is 0, or if this is not equal to 0, there are two cases. Then the remainder is 0. Then the remainder is non-zero. Basically, the remainder will depend on this quantity. If the remainder is 0, it means what? See, if error is 0, then that's not a problem. But if error is non-zero and remainder is 0, it means what? The receiver will say it is a valid code word, but still there is an error. But receiver will not be able to detect that error, right? So if I say that, let's suppose there is non-zero error, okay? If I say that ex upon gx, if this is 0, then it means the remainder is 0. It means the receiver will say it is a valid code word. Will say that it is a valid code word. If this is not equal to 0, then receiver will say able to detect error. So basically receiver will say there is some error if this is not equal to 0. But if this is 0, then receiver will not be able to detect the error, right? Receiver will not be able to detect the error. Is this clear to everyone? Okay. Now, since the receiver will not be able to detect the error in this case, then you can say that this case is dangerous, which means if gx is if this ex is divisible by just gx, then this case is dangerous. So basically, if you actually want to detect the error, if we want to detect the error, then gx should not divide ex. This is the concept that is very important. If you actually want to detect the error, then this should not be the case. Then gx should not divide ex. Now let's just understand this bit carefully. Okay, so let's see this question. What they are saying: which of the following gx values guarantees that there will be a single bit error will be caught? Tell me which of the following gx. See, does xq guarantee single bit error means what? Can anyone tell me what does the single bit error? Single bit error means error will be of this form: x power I. 2 bits error means x error will be at 2 positions. 3 bits error means error will be at 3 positions, like that, right? So if there is a single bit error, then it will look like this. So will this gx will be able to divide this x power I or not? Suppose that I is 4, which means this gx will be able to divide the x power 4, right? The remainder is 0. I'm writing the remainder, okay? So since this x cube can divide this, can definitely divide x power 4. That's why x cube will not be able to detect x power 4, will not be able to detect able to detect errors at position like x power 4, 5, 6, like that, right? It will not be able to detect these kind of errors. Now tell me, can x plus 1 divide this x power y? Let's just check. Okay, suppose there is a single bit error, which is, let's suppose, x cube, and I have the divisor which is x plus 1. Can this divide x plus 1? Can this divide x cube or any x power I? So it will be, okay, you will be writing x square here, x cube plus x square. I think this is 0, and then you writing x square, and then maybe plus x. So this will be x square plus x, and then this will be 0. Then finally you will be writing x, and then I think plus 1. There will be x plus 1. Then ultimately there will be some remainder, right? Which is 1. So basically, I mean, you do not need to do all of this. For x plus 1, actually things are very pretty simple. I will tell you that how. See, for x plus 1, let me just tell you why the things are simple. You do not need to even check the division. Tell me, if there is some polynomial, let's suppose I take some polynomial which is I mean general polynomial, I'm taking x minus 2, x plus 5, right? Something like this, right? Tell me that can x equal to, is x equal to 2 satisfy? maybe let me ask in this way, can x minus 2 divide this px? Can x minus 2 divide px? Or will x minus 2 divide px? Then what you will say? Yes, it is dividing actually. Or there is another way of checking, which is this: you just check p2 equal to 0 or not, right? If this is 0, that means x minus 2 must be the factor. Then only after putting 2, you have got the 0, right? So x minus 2 must be the factor, then only you must have got these kind of things. So if I want to check whether x plus 1 is dividing, okay, x plus 1 divides x power k or not, then what can I do? I can put x equal to minus 1. Here minus and plus are same, so I can put x equal to 1 in x equal to x power k, and then it will be 1 power k. So this is 1. So always you are getting 1 as reminder. So this 1 will be the reminder. You can try with this. I mean, we have just tried and we were getting 1 as reminder, right? I mean, that will be x plus 1. So x plus 1, and finally 1 will be the reminder. So basically you can try it, and there is another way of checking the reminder, which is just put that x value. Okay, if you want to check but just x plus k, x minus k, this is easy. But if you want to check for x square, for x cube, okay, then the things are difficult. But for x plus 1, actually things are very easy. Okay, so for x plus 1 you can directly put 1 and then you can check the remainder, right? Cool. So x plus 1 will not be able to divide any x power I, because the remainder will be 1. So since it is not able to divide, that's why x plus 1 can detect that error. See, if you are able to divide, then it is a problem. Then you will be getting the 0, then it will not be able to detect the error. If this gx is able to divide my error, then this gx will not be able to catch that type of error. If it is not able to divide my ex, then it can catch that type of error. Okay. For example, let's just see quite many examples, and then you will understand this very clearly. Okay. So let's just see more examples. Let's just see this example. Given a generator x power 5, which of the following error it cannot detect? Okay. Tell me what is the answer. This is MSQ. I hope all of you have put the like button so that it is getting recommended to others. Okay. So please just like this session, and after this session, please just comment it out, because it is just encouraging for us. See, if you comment it out, then I think one thing I can definitely promise to you, that if you show us that you are liking these sessions, if you show in the comment section after the video session has been ended, after the live session has been ended, then it definitely encourages us, and then definitely we will put more of the efforts in the next upcoming marathons for the other subjects. Okay, so we will bring all the concepts in one marathon if you just support us. So actually, we will anyhow be bringing, but if you just show us some support, then it is very encouraging. We will be just putting the more efforts. That's all. There's a human nature. I cannot do anything. Okay. So given a generator x power 5, which of the following error it cannot detect? The x power 5 divide x cube? No. So it can detect. It can detect A, right? See, x power 5 cannot divide x cube. So it can detect A, it cannot detect B, can it detect C? Yes, because you can take x power 5 common, right? So since x power 5 here, it cannot detect which is A, because x power 5 can, because x power 5 cannot divide x cube. If it cannot divide, very good. Can it divide x power 5? So it cannot detect this. And if you just simplify it, it is x power 5 common, x square plus x power 5. Then yes, like x power 5 can divide this also, so it cannot detect it, can divide this also, because you take x power 5 common, x cube plus x power 4 plus x power 5. It can divide all of this. That's why these are not the answer. They are saying it, okay, it cannot detect, it cannot, okay, it cannot, they are asking cannot detect. Then cannot detect is basically BCD, right? It cannot detect BCD. I hope you have understood GCD, right? Okay. Let me know if that is fine. You have understood everything. Cool. Now, should we move to the next thing? Let's just move to the next thing. Let's take this MSQ. What they're asking, if gx equal to 1 plus x, then it can or cannot uh, detect errors of which form? Double bit error can be detected by this. Can 1 plus x detect the double bit error? Double bit error means x power x cube, I mean sorry, x power I plus x power j. This is called double bit error. Can 1 plus x, see, for 1 plus x things are very simple. You just put x equal to 1 and check the remainder, right? Check the remainder. What is the answer here? Double bits error cannot be detected. See, for the double bit error, x power I plus x power j, if you put x equal to 1, you will be having 0. Since you are having 0, it cannot detect. So that's why it is true. Single bit error cannot be detected. For the single bit error, you are having the remainder 1. Since you are having the remainder 1, that's why it can detect actually. So cannot, that's false. So contiguous 2 bits of error cannot be detected. Contiguous 2 bits of error means x power I plus x power I plus 1. They are saying cannot be detected. Any double bit error cannot be detected actually. So contiguous 2 bits of error, yes, it cannot be detected. So that's also true. All single bit of error can be detected. All single bit means x power I. Okay. Can be detected. Yes, they can be detected because the remainder is non-zero. If remainder is non-zero, then the things are good. So A, C, D is the answer. Right? A, C, D is the correct answer. Okay. So see here, A, C, D is the answer. Now let's do this question. Let's suppose this is the error, and so now just tell me which generator can detect this error. Okay, which generator? Can this detect? Can this detect like that? You need to tell. You need to divide actually. If it is dividing perfectly, then it cannot detect. So actually for 1 plus x things are easy. You do not need to divide. The remainder will be 1. Since the remainder is 1, it can detect. It can detect. Here it can also, it can, since it is x power 11, how can it will be dividing x power 10? So since it can also not divide, that's why it will be detecting. Can 1 plus x power 9 divides this x power 10? That we need to check, right? 1 plus x power 9, which is basically x power 9 plus 1, can it divide x power 10? That we need to check. Let's just check it. Okay, if there is a confusion, just do a division. Okay, very simple. So this is x power 10 plus x, then it will be x, right? So remainder is x. Since the remainder is x, which is non-zero, that's why it can actually detect. It can detect, right? Check x power 10, x power 8 plus x power 9. Check if x power 8 plus x power 9 divides x power 10 or not. So it is x. Let me write x power 9 plus x power 8 this. Then this will be x power 10 plus x power 9. It is x power 9. And then you will say that, okay, plus 1, then it is x power 9 plus x power 8. Since x power 8 is remainder, so it can also detect. Remainder is non-zero. Can it detect? Obviously no, it will be dividing it fully. No, sorry, the x power 7 cannot, sorry. What is the x power 7 is the generator. Let's just check. If you divide x power, if you take x power 7, x power 10, you will be dividing by x cube. Yeah, it will be dividing perfectly. Sorry. So it will be dividing perfectly. So that is why it cannot detect. So which of the following can detect? A, B, C, D. It cannot detect. E cannot detect. Okay. Is this fine to everyone? You just take the division and see what you are getting as an answer. Now, maybe you can do this question. Let me do one of the gate question first, which is this one. Okay, this question, let's just do this first, and then we will see some other questions. Tell me what is the answer that you are getting for this particular question. This is a nice question. Just tell me what is the answer that you are getting here. Okay, I hope you have solved it. So Pratik is getting C. Yes. So C is the answer. So let's see why. So GX is the generator polynomial that used for the CRC checking. What is the conditions should be satisfied by GX to detect odd number of the errors? Okay, odd number of error means this is maybe 1 bit of error, maybe like 3 bits of error, like that, right? Odd number of errors. So if it is odd number of errors, then 1 plus x can definitely detect it. Okay, because if 1 plus x, if gx is equal to 1 plus x, if gx is equal to 1 plus x, then it cannot divide it, because the remainder will always be 1. Either it is 1 plus x, or gx is having a factor of 1 plus x, because if 1 plus x cannot divide it, then something which is having the factor of 1 plus x can also not divide it, right? So if gx is having a factor of 1 plus x, then it will not be able to divide the odd number of errors. So that's why 1 plus x is a factor. If it is a factor of gx, then you can definitely detect it. Yes, so everyone is getting C as an answer. GX does not divide this. So these are actually just to confuse you. I mean, GX has odd number of terms. No, that's not. If GX is having odd number of terms, let's suppose GX itself is x power I plus x power j plus x power k. Then DX can definitely divide this, right? It will not be able to detect this odd number of error, right? Okay. GX does not divide this where k does not exceed the frame length. Actually, this frame length and these things does not have any interrelated concept. So that's why this is wrong. GX contains more than two terms. No, if it is having more than two, if GX is, this is the error that you have. If GX is exactly equal to this error, which is having the more than two terms, then obviously this can divide, which means it will not be able to detect this error, right? Okay. Now this was the CRC. This is the answer that I have put on the GATEOverflow. I think some people are talking about it, and yes, this is one of the, one of the nice answers that I put from my side, because it just took, I think, maybe one day to read all of this concept and then come up with the explanation. That see, writing the answer is always very tricky, because you have to write in such a way that is very concise. You cannot put a video there. You have to write in the text. It should not be too long that people are not even reading it at the first place. So that's why it is very tricky, very precise, that how to write the answers. And from the GATEOverflow only, like when I started writing the answer, then only I got more interest in the teaching, because at that time, like maybe like I like the way that I was writing the answers on the GATEOverflow. I was putting my thoughts. So teaching is also putting your thoughts in the visual form, and writing the answers is also putting your thoughts. So basically, that's how the dots get connected, right? Okay. Someone is asking, Tadkappa is asking that what if there is an even number of errors? If there is an even bit of error, which means if this is x power I plus x power j, then 1 plus x will be having a remainder 0, so it will not be able to detect. Maybe there is something else. I mean, see, there it depends on the options basically, right? So 1 plus x will not be able to detect first of all, but maybe it depends on the option. We need to check whether it is dividing or not. Okay, just like other questions. See, for these questions also we have checked whether it is dividing or not. We have actually went about dividing, and then we have checked whether it is dividing or not. So you need to check with the division actually it is dividing or not. Okay, so now let's just start our network layer. Network layer is very nice. I mean, very nice and very, I will say, easy and scoring. So let's just start network layer. And in the network layer, we will be covering everything that is required, which means I will be covering subnetting, supernetting, all of these concepts, subnetting, IP addressing, supernetting, and obviously the gate questions based on these. And then we will be like once we cover this, then we will be covering IP fragmentation. Then we will be also covering distance vector routing protocol, and we will also be covering LSR, which is link state routing, and PYQs based on those. Okay, so PYQs on this. I think that is all network layer required, right? IP fragmentation and IP header and these things. And I think that sums up the network layer. So I have these things in my mind. Let me know if you want anything else to be covered. I don't even think that anything is remaining. Okay, if there is something, then you can let me know. Should we start after 10 minutes? Let's start at 7:26. Okay, 10 minute of break. So meanwhile, if there is anything that you want me to cover, if there is anything, any feedback that you want to give, then you can let me know. If you are liking the session, then please hit the like button and also share with your friends. One last thing, once the video is over, then please drop a comment that how you are liking our efforts. If you are liking it, then we will definitely get encouraged, and then we will definitely be putting more efforts. That's the whole idea, right? So it's not like that we will not be putting the efforts, but it's the human nature. Like if you just encourage us, then we will be doing it more. Okay, let's meet at 7:26. Hi everyone. So let's get started. Learn with me is asking. So TCP will not be covered today. See, I am ready to open cover it today. So we can have we can either cover it today or maybe we can cover it early morning. I mean, we can cover it from 8 to 10, so or 8 to 11. So it will be upon you. See, I think I mean I think I'm not sure if the graph theory will take how much time, but tomorrow we have the graph theory session, and since we are going in bit detail to be very honest, so that's why it is taking a little bit more time for me. And CN is a big subject, right? It is a huge subject. So but we are covering each and everything in bit detail. So we can have one option. So currently it is 7:30, right? It is 7:29 or 7:30. So we can run this class till 9:30, and we should be covering the network layer, or maybe 9:30 or by 10. By 10, no, we should be covering the network layer. In the remaining in the remaining time we will covering the 10. By the 10 we will covering the network layer. Then I think in the morning we can start by 8 a.m. Okay, 8 a.m. tomorrow to 10:30 a.m. we can cover the remaining the transport layer, right? So transport layer is actually a small portion. Transport layer is a small portion, so we can cover it tomorrow in 2.5 hours. Transport layer and obviously the application layer. Is this fine? Let me know if this plan suits you. Tomorrow is a graph theory session. It is supposed to start at 10 a.m. But since we are covering, if I take some of the time, then after 1 hour of me, Deepak will start. And you know that how Deepak how Deepak teaches, right? He is in very much flow, so he is very fast in the sense like he repeats till you get it completely, and also he is actually faster than me. I do not have that much energy somehow. Okay, I cannot speak 2 hours continuously. I need to take a break for water. I need to take a break to breathe. But Deepak is very different. All of the Deepak sessions is just like marathon. I mean, his usual class are just like marathon. So for the marathon, he do not need to do for extra preparation just like me. So anyway, okay. Can you please make time a little later? Okay, maybe we can start by 9 a.m. something like that, right? We will just discuss like at what time we should be starting, and based on that we can schedule it. So let's just continue with the network layer. Just give me a second. I do. Let me just bring the slides that I have. Okay, just 1 second. Network layer slides are in this folder. Yeah. So let me know meanwhile if you have any other question to me, and then we can just start. Right? Cool. Yes, Deepak is just like Usain Bolt. Or you can make a session for a graph part and then do the TCP session later. We can just decide, not a big deal. Okay, but I can promise you one thing, that we will be covering everything in the marathon. Whatever is promised, that we will be covering in the marathon. So it's not like that if time is not permitting that we will not be covering. Okay, so it will not happen. Okay. So I'm just importing my slides. Just give me one more minute maybe, and then we can start. Okay. So let's just get started. Cool. The slides are now imported. Okay. So let's start with the network layer. Let me know if you have any doubt till this point, and then we can start. Okay, there are some doubts. Sandeep is asking, sir, for the subjects you will not be covered in the marathon, can you suggest videos on the channel? We should refer later. Mostly we will be covering all of the subjects. The schedule that we have published, it is just before the All India test, but after the All India test we will be covering more subjects. Don't worry. Arnav is asking, sir, can you take time and make concepts digest? You also take time and okay. Thank you, Arnav. So Himanshu is asking, sir, these lectures will be available in the, yes, these lectures will be available. Learn with me is saying, learn with me, what is actually your name? Can you please tell me? I mean, like I am not able to recognize you. Maybe in the future I will be able to recognize you. Okay. So he's saying that I'm really thankful to you that you are focusing on the analytic concepts part, which is crux of understanding. Yes. Thank you so much. Learn with me. Okay. Let's just get started now. So the first portion that we will be covering is subnetting, supernetting, and IP addressing in the network layer. Then we will go to the IP fragmentation, then these two topics. Okay. So IP addressing and subnetting. Let's just cover this first. Now there are two types of addressing that you might also be knowing. One is the classful addressing, which means that here you have the classful notations: class A, class B, class C, class D, class E. And another one is classless addressing. So in the classful addressing, which we are currently seeing, is basically saying that class A is having the first byte as fixed. I mean, you cannot change this byte and you can change these bytes. So which means in this particular kind of class, you are having, since these are 888 24, you are having 2 power 24 hosts. I mean 2 power 24 IP address or minus 2 host. I mean minus 2 plus 2 does not matter, but yeah, minus 2 hosts. These many hosts you are having, right? And similarly, you can calculate the number of hosts for the class B, which is 2 power 16. For class C, it is 2 power 8. The thing is that class D and class E is actually reserved. These are not used to allocate the host. Now, the thing is that for the class C, you have two less hosts, which is 2 power 8 only. But for the class B, you have too many hosts, which is 2 power 16. 2 power 16 is too many. So, because of this problem, I mean, either you have too less or you have too many. Because of this problem, we go to the classless addressing. Right? So classless is very nice addressing in which you do not have any restriction that you need to allocate from any of the class. Let's just see the classless addressing, which is very nice addressing. Here we have the prefix length as \n, right? So there is no class, hence the network ID is not implicit. So we need to specify the prefix explicitly. So here what do happens? Let's suppose you are saying /n. It means that n bits initially are fixed and that are part of your network address, and later bits are called suffix, which are part of your host address. I mean you can change those bits and you can have any other IP address that you have. Okay. So this is the first address that you have that is having suffix 0. This is the last address that you have that is having suffix 1. First address is called network address, and this is called directed broadcast address. Right? Okay. Now let's directly jump into the questions and let's directly do the questions maybe. So what they are saying is that, let's see, they are saying that two computers C1 and C2 are configured as follows. C1 has some IP address. So C1 is having some IP address which is 203.197.2.53, and there is some network mask that C1 is having which is 255.255.128.0. This is the network mask of C1. Now C2 is having some IP address which is 203.197.75.201, which is also having some network mask which is basically 255.255.192.0. So see, what do I mean by that? It is having IP address and network mask. Do you like, how many of you use Windows or do you use Mac or Linux? Do you use Windows? I mean, in Windows, I know that the GUI, you click on some IP configuration or something. I mean, you go to the control panel and you click on the IP configuration, and it's actually shows, I mean, every laptop has IP address. It also has the default network mask, right? Default subnet mask. So basically, the default subnet mask is given to us, and it is very, very needed. Who does provide this default mask? Can anyone tell me? When your system is getting booted, who is going to provide you default mask? Have you heard of DSCP or the boot P? What it does, it tells you the IP address. along with the IP address, it also tells you that what is your default mask and default gateway and these things, right? It also give you some of the other things that you required to communicate to the internet. Okay. So this is the IP address that you have. This is the network mask you have. This is the IP address. This is the network mask that you have for this C2. Now what they are saying, C1 and C2 assume that they both are in the same network. C2 assume that C1 is on the same network, but C1 assumes that C2 is on a different network. That's what they're asking. Let's just quickly do this question. Not a hard question, just an easy question it is. So see, here you are having network mask of 128. 128 means that 1 followed by 7 zeros. 1 followed by 7 zeros, right? And 192 means 128 plus 64, which means 1 followed by all are zeros, 6 zeros. Okay. So here you are saying that latest, most significant 2 bits are fixed. Here you are saying only just 1 bit is fixed. If you see the 1 bit, which is 0, right? So C1 says that I am in a network which is having starting address of this and ending address of 203.197.1. Sorry, this is 0, which is fixed, and then you can have all of these as 1. Whatever, right? I'm writing in binary and decimal mix format, but I hope you understood. Okay. So this is what C1 is saying, that I am in a network that start with this and end with this. Let's just see what C2 is saying. Okay. So C2 is saying I am in a network that start with this. Can you tell me that what is the 75? 75 is actually having not having 128 actually, right? And it is having 64. So this is 0 1. That is actually starting with 0 1. And then all are zeros. 1 2 3 4 5 1 2 3 4 5 6 7 and 8. And then 203.197 dot, this is 0 1 is fixed, this is 0 1 is all are ones. Okay. Now see, it is from 0, anything that start from 0 to anything after like anything that start from 0, basically C1 is having a super network. C1 is saying that I'm in a bigger network. So let me go to the next page and let me show you that what does the C1 has and what does C2 has. See, C1 is in the network which is saying that I'm starting, so this is fixed, I'm starting anything that start with 0. So anything that start with 0, I'm in that network. Okay, I'm in dot 0. So I'm in the network. That's a very big network, right? So anything that start with 0. Now like I will tell you in the subnetting. So basically if you choose one more bit, okay, from this network, let's suppose you choose this one more bit. Now you can divide this network into 2 parts. You will say that is starting from 0 0, this portion is starting from 0 1. That's called subnetting, right? See, all of this, I'm not sure if you're following or not. All of this is starting from 0, right? That all of this is starting from 0. Now I divided into 2 parts. It is this 0 is fixed. Okay. So this is the C1 network. C1 belongs here. C1 is here. Now C1 might be here. C1 might be here. We will just check where is the C1. So, but C1 could be anywhere. Okay. But this is a network of C1. C1 is in this network. And now if you choose one more bit, this is 0 1, 0 0 and 0 1. Now C2 is saying that 0 1 is fixed. Now anything that starts with 0 1. So basically C2 is saying that this is my network, right? C2 is saying this is my network. Okay. So this is the C2 network. This is C2 network. Is here. Right? Cool. Have you understood this? C1 is in this network and C2 is in this network. Now, C1 definitely thinks that C2 is in this network. The whole network is of C1. So C1 will say that C2 is definitely with me, right? C2 is in my network. Is this clear to everyone? C1 will definitely say that C2 is in my network. Now we need to check whether C2 is saying or not. That's another story, right? We need to check whether C2 is saying something or not. So one thing is for sure that C1 will say, maybe I can go to the next page and I can tell you that, okay, C1 is saying that C1 says that C2 is in my network. Okay. Now let's just check whether C2 is saying that C1 is in its network or not. It will depend where is this C1. C1 can be anywhere here because this is the whole network of C1. We will check the IP address in just a moment. But C1 could be here. C1 could be here also. If C1 is here in the first half, then C1 will say that okay, C2 will say that C1 is not in my network. If C1 is in this half only, then C2 will say this it's also in my network, right? What's wrong with this? So the IP address of C1 is basically this one .2.53, which means, let me just copy that to on the same page. Sorry. Okay, let me just write it. C1 IP address is 203.197.2.50. 203.197.2.50. C1 IP address is this, right? Now tell me, what is this 2? 2 means 0, 0, 0, 0, and then finally it is 1, something like this, right? 1, 0 basically. Now, since it is starting with 0, 0, that means that anything that starts with 0, 0, that is here. So C1 is here actually, right? So C2 will say C2 is here, C2 is here, C2 is here, and C1 is here. But for C1, everything is one network. For C2, this is just one network. So C2 says that C1 is not in my network, right? Because C1 is here, and for C2, this is just one network. But for C1, the whole thing is one network. So it also depends that where is C1. So C1 will say C2 is in my network, but C2 will say C1 is, C2 is not. C2 will say C1 is not in my network. C1 assumes that C2 is on the same network. C2 assumes that C1 is on different network. So that's why C is the correct answer, right? Now let's just twist this question a little bit. Okay, so I hope you are understanding. Let's just twist this question a little bit. Now instead of giving you C2 IP address as this, let me take C2 IP address, which is something. Let's suppose maybe let's suppose it is 65. Okay, I want 01, so that's why I'm writing 65. Yeah, 65 will work. So let's suppose C1 IP address is this. Then just answer this question. If this is 65, can you answer this question now? Let me write 65 here. Now it is quite interesting question, right? I mean, see, most of the people who are just doing the rote learning, they might just say that okay, C1 is in the bigger network. I'm sure if I just give this in the all India test, okay, I'm almost sure if I just replace this C1 with 65, I'm almost sure that all of the like 99% of the aspirants will say the same answer. But here now C1 is in the bigger network, but the actual placement is here, right? Actual placement of C1 is here. So that's why C2 will also say that C1 is in my network. I mean, C1, C2 both will say that they are in each other's network, right? For the C2, because C1 is in its network actually, it is for C1 the network is bigger one, that is okay, but both are in that smaller network. So that's the thing that will matter. Okay, so I'm almost sure that if I replace this with 65, then just because C1 network is bigger, people will say that C1 is people will say the same answer. The C1 will assume that C2 is in my network, but C2 will assume that C1 is not in my network, and that is the wrong answer. Let me know if I'm correct or wrong. So if I replace this with 65, how many of you might have done this mistake? I'm not saying you will do it, but might have done this mistake. Okay, great. So let's just continue. Yeah, just a second. So C is the answer, right? Now let's just continue with this question. Host X has IP address this, and it is connected through two routers R1 and R2, right? Host X has some IP address which is connected through two routers R1 and R2 to Y. See, the language is very important here. It is connected to Y. It is connected to Y, but through two routers, which means it is connected to Y through two routers R1 and R2. Okay. Don't make the diagram something like this. It is connected to two routers. No, it is not connected to two routers. It is connected through two routers. Okay, not like this. Don't make the diagram like this. It is not connected to these two routers. So that's why the language is actually important, what they are saying. Okay. Now X is having some IP address which is 192.168.1.97. Y is having some IP address which is 192.168.1.80. Router R1 has the IP address which is, see, this router is connected to two interfaces. Do you remember I told you that this will be having two IP addresses, right? Now router R1 is having two IP addresses which are given like this, 192.168. So actually I think it is not given that which IP address is of which interface. But just for the sake of assumption, I'm saying I'm just writing it. Maybe I'm wrong. Okay, for now I'm writing it. Let's suppose this IP address 192.168.1.135 is of this this interface, and the another IP address which is given is 192.168.1.110. It is of this interface. Okay, for R1. Similarly for R2, it has two IP addresses. Let's just assume that these two IP addresses are also in the order, which means R2 is having this IP address 192.168.1.67 for this IP, this interface, and then 192.168.1.1555 for this interface, right? I mean, I may be wrong in the sense these two might be interchanged. I do not know. Similarly, these two might be interchanged. It is not actually given in the question. So let's just see, like, I mean, what they are asking, and do we actually need to know that which interface is having which IP address? Actually, I might be wrong. Okay. The network mask used in the network, so they all are using the network mask which is 255.255.255.224. 224 means 128 plus 64 which is 192 plus 32 which is 224. Okay. So all are using this network mask. Now they are saying which IP address should X configure its gateway to. See, for X the gateway is definitely R1. Now R1 means that, see, the scenario is like this, that X is connected to R1, it is connected to R2, it is connected to Y. Now the default gateway is definitely R1. Now what is the IP address of this? This IP address is default gateway, and that is what they are asking. This IP address is default gateway, right? And that's what they are asking. Let me know if question is clear to everyone. So actually what you need to do here, you basically need to check what should be the IP address of this interface, and you have two options, right? You have this one and this one option. So I don't think we need this R2 detail at all. Maybe that is required for the next question. Maybe okay, they have just asked this question only. They have not asked the linked question. So let me just copy this. That R1 IP addresses are these, X IP address and the network mask. So see here that R1 IP address could be of the two options, which is basically, let me write it here. So could be one option is that, I mean, this interface actually I do not know. I'm just writing it randomly. It could be 192.168.1.135. Similarly, I do not know IP address of this interface also, but I'm writing it randomly, which is, I mean, I'm writing one of this is 192.168.1.11. And this host is having some IP address which is 192.168.1.97, and it is having some network mask which is basically 224, right? At the end it is 224. So basically it is having some network mask which is 255.255.255.224. 224 means, as I told you, it is like, actually these are very popular number, 128, 192, 224, and then if you add 16 here it will be 240. So in the networking, I mean IP addressing, these are very popular number, 128, and you add 64, 192, and then in that in the network mask actually it is these are popular numbers, that's why I remember it, 224, 240, and then you add, okay, you have add 16, then you add 8, 248, then you add 4, this is 252, then you add 2, this is 254, and then 255. Anyway, so these are some popular numbers, like start from 128 and then you keep on adding in the network mask. Okay, for the network mask, these are the some numbers which are frequently used. So anyway, this 224 is just 128 plus 64, which is 192 plus 32. Now it is 2. Okay, which means they are saying that latest or the most 3 bits are part of the network ID. Okay, so let's just see that which should be the interface. I mean, the interface ID should be which IP address. Okay, so see here, this interface is always, see, this is just one network here. Okay, this is one network, and R1 is part of that network. R1 is actually being a router, it is always part of all the networks that it is connected to. So the number of networks, let me first tell you. Can anyone tell me number of networks here? We have done this question from the previous session. Can anyone tell me number of networks here? Just let me know. How many networks do we have? Three. 1, 2, 3, right? 3 networks. So R1 is part of this network. R1 is also part of this network. R2 is part of this network. R2 is also part of this network, right? So these are the 3 networks. These are the network 1. This is network 2. This is network. These are the 3 networks that we have here, right? Okay, great. Now, see, here this interface, whatever I give IP address, maybe this or maybe this, actually I do not know, right? Maybe this or maybe this. Whatever IP address I give to this interface, it should be part of actually this network, okay? This network, it should be part of this network, which means this X is saying .97, which means 97 means it is lesser than 60, greater than 64, but lesser than 128. So 128 is 0, 64 is 1. So if you subtract the 64, it will be 3, and then this will be 3, 33. Then 32 is also 1, right? And you do not care about other numbers, right? Because I just need the most significant 3 bits. So 97 is this, which means 0, 1, 1. So basically this network is saying starting with should be 0, 1, 1, whatever else you do not care. Let's just check whether this is starting with 0, 1, 1 or not. Is this starting with 0, 1, 1? No, right? Definitely it is starting with 1. So it is not starting with 0, 1, 1. Is this starting with 0, 1, 1? Yes, 0 and then 64 and then 32, right? Because it is greater than 97. So it must be 0, 1, 1. So basically it is starting with 0, 1, 1. It is starting with 1 or something, right? Since it is starting with 0, 1, 1, that means that it is a part of the network of X. So the final answer is this. I mean, you should be actually swapping these two, right? Let me know if that is fine to everyone. Is this fine? How we are checking whether this interface is having which ID? See, X is a bigger network. X is in the bigger network, and from that network, we give first address to network address, last address to directed broadcast address, and some address in the between to the interfaces also. Okay, from that network. So we are giving some address to this interface, and this is the address that we should be giving. So 110 should be the answer. .110. So B should be the answer. Very nice question, right? Okay, you haven't got it. See, X is in which network? This is .97. 97 means 011. I'm just interested in initial 3 bits. Okay, so it is 011. It is dot one something, but it is this 110 is actually in the binary. It is 011. Okay, it is also 011. It is one something, and this X is basically 011. So basically X network is X network. Let me write the X network. It is 192.168.1.97. This is X IP address. And using the network mask, you can say it is ranging from 192.168.1.110, and these bits you can change basically, right? All zeros to all ones. One, two, three, four, five. All zeros to all ones you can definitely change, which means this is the X network. X is in this network. Now this X is connected to router R1. Okay, and that is connected to R2, which is connected to Y. That is fine. Now you need to check what is the IP address of this interface. This interface, as I told you, that has to be part of X address, X network. See, this is how we divide the networks. So this is one network, which means X and this interface are in the same network. That's very important to understand that X and then this interface has to be in the same network. Okay, if X has to send out of the network, it will send the first packet to the R1, and R1 is in its own network. Okay, R1, see, very interestingly, R1 is basically in the network 1 also, in the network 2 also. Okay, X has to send first packet. If it wants to send something outside R1, outside its own network, it will send a packet to R1 first, and then R1, being a default gateway, it will send that packet to someone else, right? So X and R1 are in the same network. That's what I'm saying. So which means X and this interface in the same network. So whatever, so this is the X range. I mean X network range. Now this interface, whatever you have here, should be in this range only. So if you take, you have two options here, which is 192. You have two options here: 192.168.1.135. Another option is 192.168.1.110. These are the two options that you have. Now, out of these two options, which one is a part of this network? The X, this is the network of X. This is the network of X. Now tell me, out of these two IP addresses, which IP address is a part of network of X? Okay. So now I hope you understood that what is the correct answer, right? See, okay, I do not know if I am able to convince you or not. Let me just drink some water, maybe. Okay. Yeah, right. So basically, this 110 is a part of this X network. That's why I will give 110 to this particular interface. So X will send to 110. Now I hope that is fine to everyone. Great. Now let's just extend this question little bit. I mean, not extend. Let's just see if I can determine for everything. Just like 110 I determined here. Can I determine for every other number? Okay. So this IP address I know. I think everything is having the same initials. Dot one. Okay, everything is 192.168.1, right? So everything, every IP address in this question is starting with 192.168.1. So I will be just skipping it. Okay, let me just skip it. It is .97. We just figured out that this is .110. We just since it is .110, it has to be what is the other option? 135. Similarly, for R2 also, they have given two options. Okay, they have given two options for R2. Let's just quickly see which option is correct. So by IP address is given to us, I think, is .80, right? By IP address is given to us .80, and the network mask is also given to us, which is 224, which means 3 bits should be fixed. 224, which is actually 128.60 plus 64 plus 32, right? Yeah. So 80 means 128 is 0. See, you never need to convert. You are seeing some smart way to calculate these type of questions. You never need to convert 80 to the whole binary. You just check the most significant bits. 128 should be 0, 64 should be 1, and then if you add these two, this is 96. So 32 should not be there, right? So it is .010. Now let's just check with R2. Okay, R2 is having two options. R2 is having two options, 67 and 155. 67 and 155. Let's just check if this option is working. So 155, does it have 010? No. So 67 should be the answer here, and 155 should be here. So actually it should be something like this. This is .67, this is .1. Right? Let me know if you have understood this completely. So now we have determined the IP address for every interface. And then I will say that, see, this particular thing is one network, right? this particular thing is one network, this another particular thing which is this one, this particular thing is one network, and this particular thing, maybe let me use another color, this particular thing is one network. So these are the three networks that I have. Cool. Is this understood to everyone? Okay, 67 was having three initial three bits, or the most significant three bits were 0, 1, 0, 1, 0. 135 is having most significant three bits are, what are those most significant three bits? 1, and then 0, and then this is, okay, 0, 1, 0, 0. 110 is having most significant three bits. I mean, you can calculate the most significant three bits, right? So based on the most significant three bits, we are deciding. Okay. Okay. Let's just move further. Now let's see this question. This is also very, very good question. Okay. Let's solve this question. What they are saying, suppose computer A and computer B has the IP addresses this respectively, and they both use the same network mask N. Which of the following N given below should not be used if A and B should belong to the same network? So they are saying that A and B has the IP addresses. A has some IP address, B has some IP address. A has some IP address which is 10.105.1.113. B has some IP address which is 10.105.1.91 respectively, and they both use the same network mask N, which means backslash N, they both are using. Which of the following value of N should not be used such that A and B should belong to the same network? Right? Do you want to try this question? Okay, let me know what is the answer. Just try it for a minute and let me know what is the answer. You can convert 113, you can convert 91. So 113, if you convert to binary, then I can help you if you want. Otherwise, you can definitely convert it. So it is basically 64 plus 32 plus 16 plus 1, right? So 113 is 64 plus 32 plus 16 plus 1. 91 is 64 plus 32 plus 16 plus, no, 32 will not be there. 64 plus 16 plus 8 plus 2. So anyway, you can convert it and then let me know what is the correct answer. So let's just check with this option. If this is saying that these should be same, and then you can have everything. So anything here in the last octet. So if you are using this, then they will say that yes, both are in the same network. So that's allowed. They are saying not be used such that not in the same network. 128 is also fine. 60 till 64 things are matching. 192. Let me know if 192 is fine. 192 means 128 plus 64. So 128 is not there in both of them. 64 is there. Basically, both of them are starting with 01, 01. So initial 2 bits are fine. But if you take initial 3 bits, then it is a problem. It is 0, 1, 1. It is 0, 1, 0. So that's why it is a problem. Okay. Yeah, D is the correct answer. Now let's do this question. This question is also very nice question. What they're saying, an ISP has the following chunk of CIDR IP addresses available with this. So ISP wants to give half of the chunks to the address organization A. So see, they have given some pool of IP addresses, and from this they want to give some half of the IP addresses to some organization, and which is A. So these are the pool of the IP addresses that it has. Now half of them they want to give to A. Okay, half to A, quarter to B, quarter to B, and retaining remaining with itself. So basically, whenever you have the pool of IP addresses, let me draw with this pie chart. Okay, this is the popular chart using which we can draw the all set of IP addresses. This is a pie chart, right? Now, what you can do, if you want the half, then you can divide it into two parts using fixing the one bit. Now, what you can do when you are fixing the one bit, then this is just one half, this is another half. What you can do, you can say that either the one of the half is for A, one of the half is for B, which means I mean not for B, but yeah, for A. So you can say that this is for A, or there is another option, you can say this is for A, right? Is this fine to everyone? Now you want to give quarter to B. So if you have chosen this as an answer, okay, so if you have chosen this as an answer, so you say either this or this. Now from this you will say that either you divide it, you fix one more bit, you divide it into two more parts, right? Then you will say maybe I can draw it. A second. So basically here also you have two options. Maybe you divide it into one more half, you give it to B, or you give this to B, right? Similarly here also you have two options, right? You divide this into half, you divide this into half, you give this to B, or you give this to B. So these are the actually four possibilities that give half of the IP addresses to A and quarter of the IP addresses to B, right? So finally you have the four possibilities where you can have half of the IP addresses to A and quarter of the IP addresses to B. Now whatever they have in the options, one of the possibilities should be matching. I mean they are saying that which is a valid allocation. So answer maybe containing this, maybe containing this, maybe containing this, maybe containing this, because all of them are actually valid, right? Okay, so let's just do this very quickly. Okay, it's very easy question, but yeah, still let's just do it quickly. So here let me check what is the pool of the IP addresses. Yeah, this is the pool that I have. So let me just take this pool, right, and let's just check, I mean what are the valid allocations. Okay, this is the pool, right? Slash 20 means you keep 16 plus 4 bits as it is, which means from here 1000, this is fixed, and then remaining bits 1 2 3 4 and then dot, all of these bits are free. Now if you're taking this combination, then A will get, okay, this is let's suppose 0 1, then A will get initially it will get one. I mean I'm not writing the initial portion, I'm just writing, or maybe let me write it so that it is more clear to you. 245.248.1, this is obviously fixed, right? And now A is getting 0, A is getting 0 1, and B is getting, so this is A, and B is getting 0 0, and B is getting, let me write for the B, it is getting 0, right? this combination, I mean remaining bits obviously can change to anything, right? Remaining bits can change to anything, whatever you want. So this basically allocation says that you are allocating half of the portion to A and a quarter of the portion to B. Can you write for this? Definitely. Just almost like this, almost like this. Let me write here. So A allocation is same. For B, you will be saying that you need to have one here. I mean, I'm writing all the possible allocations, not just the question. I mean, questions have not asked all the possible allocations, but yeah, they may also ask this. They may ask you that in how many number of ways you can divide such that A gets half and B gets quarter, such that all of the IP addresses in A are contiguous, all of the IP addresses in B are contiguous. Okay. So this particular diagram corresponds to this particular diagram where A is getting starting with 1. Okay, this particular diagram corresponds to this where A is getting starting with 1. Maybe let me write it. So here A is getting starting with 1, B is getting starting with 0 0. Yeah, B is fine. So A is getting to start with 1. Right. This particular allocation is basically write it here. A is getting to start with 1. B is also getting to start with 0 1. Right. So basically all of these combinations are valid. Right. Is this fine to everyone? So these are the 4 combinations in which you can divide, and all of these combinations are valid. Now you can check I mean what they have given. See, for the A, the IP the backslash that prefix should be 16 plus 5, it should be 21. For the B, it should be 22. For the A, it should be 21. For B, it should be 22. So only the possible answers are A or B, right? C and D are anyway ruled out because it is slash 22 can never work with A. Similarly, slash 24 can never work with A. So slash 21 can work with A and slash 22 can work with B. Now let's just check whether this is the correct option or not, whether A is the correct option or B is the correct option, right? So A is saying 136. 136 is actually 128 plus 8. Okay, so slash 21, which means 16 plus 5. So 5 means this is 1 and then 64. Okay, so basically for A, 164, just a second. This bit should be, okay, let me maybe convert it, this binary to decimal. 164, 32 and then 16 and then 8, right? So they are saying that these two are 1. For A, they are saying that IP address that A is having, basically this one, is basically 245.248.136 means this is 1. This is 1, 2, 3 zeros and then this is 1, and this could be anything. That they are saying A could be this, and at the same time they are saying that B could be this 245.248 dot this is 22. 22 means that you should be having this 16 plus 6 bits at fix 1, 1, 2, 3, 4, 5, and then this could be anything, right? Tell me, will this work or not? So A is ending with 1 and then B is ending with 0 0. So which kind of allocation it is? A is ending with 1, A should be this, and B is ending with 0 0, right? So B should be this. Yeah, this will work, right? So this is the correct answer, where A is this. Let's just check another options. Let's just check B and let's see if there is any problem with B. So this will work definitely. There is not a problem. Let's see if there is a problem with B or not. Okay. So B is basically 128 slash 0. So 128 means you should be having 0 here, and these bits are fixed. And this is also 128. Yeah, that's interesting. Can you have this? If you are having this, then A should be, see, A is borrowing 0, B is borrowing 0 1. A is this, right? And B is this. They are saying B is this. I mean, in the A itself, you are giving to B. That is not possible, right? Okay, people are saying D as answer. D really answer. Correct option is A, right? Okay, you are saying D answer is for the previous question probably. Okay, got it. So have you understood what is the problem with B? B is actually in option B, the organization capital B is actually taking some part of A, which is obviously not a liable option, right? So I hope you understood. Anyway, you do not need to do all of this. I mean, all of the combinations you don't need to make from the options also you can do it, but just for the sake of fun, maybe I just did it, right? So there are many possibilities. These are the possibilities, and in option A, 0 and 0 0 0 0 0, which is the correct option? 0 0. Yeah, this is the option A. Option A is having these two IP addresses. So option A is the correct answer. Okay. Now let's just start subnetting. Okay. So let's just do one thing. Should we take a break of 1 hour and then in the next lecture we will be starting the subnetting? Is this fine? So let's just start at 9:30 maybe. From 9:30 to 11:30. Network layer we will be finishing. And then we will be starting transport layer tomorrow sometime. Let me know if that will work with all of you. Or should I continue? Because you will be also having the time for dinner. Which 4 cases? These are the 4 cases that we have. Where is that question? So we have seen all of the 4 cases, right? I'm not getting, Sumant, what you are asking. So these are the 4 cases that we have, and if the options, it could be MSQ which may contain all of these options, then all of these options are actually correct. Okay. So let's start at 9:30 and we will be continuing at 9:30. So thank you everyone. Thank you so much. Take care. Bye bye. Just one request. Okay, that's very important, and that is actually needed for us at this point in time. If you, like, we generally don't say it, if you just comment on this video, it will be very helpful for us, because later the experience will get to know after the session end. Then just comment it so that later experience come to know that that this session was actually good and it was really helpful. Okay, so just comment it out. Sumant is saying that how case 1 is valid. Case 1 is valid because A is in the different area. Oh, sorry. This is 0 and 0. No, it is actually 0 and this is 1 0. Sorry, this is the typing mistake. Yeah, thanks for correcting me. This should be 1 0. Yeah, this is 1 0. And this is 1 and 0 0. So I think this is not the option A. 1 and 0 0. This is the option A. Third diagram here is the option A. This is option A. Yeah, I agree with you. So thank you everyone. Take care. Bye bye. Yeah. Yes, Sumant, you are right.